Welcome back. Today's lesson is on section 3.2, which is titled Linear Regression. We'll start with the following example. The Quick Sell car dealership has been airing commercials on a local TV station. The ads always appear during evening hours and advertise different models and price ranges of cars on the lot that week. Over a 10-week period, the Quick Sell dealer tracked the number of commercials versus the number of cars that were sold. And here is the data that was found. That in the 1 week, they ran 6 ads and sold 15 cars. And then the following week, they ran 20 ads and sold 31 cars. Week 3, they didn't advertise at all. They sold 10, and so on as we go down the list, all the way down to the 10th week in the sample. They advertised 8 times and sold 15 cars. Now, the big question. We're going to use this data and we're going to make a decision here. The general manager of the dealership decided that they can only afford 12 TV advertisements per week. At that level of advertisement, how many cars should Quick Sell be expecting to sell in the course of the week? Well, if we look at the scatter plot, you can see that there is a fairly strong linear correlation. It appears to be positive. It certainly is positive. As x is increasing, y is increasing along with it, as we would expect to have happen. However, to answer the general manager's question about how many cars we should expect to sell at 12 TV ads per week, it would be nice if we had a function to work with. And we can draw in a line of best fit. And if we trust that this is the best possible line to model the sales off of the advertisements, then we can just go with this. But my question to you is, what makes this line the best fit? And there's actually a few different answers to this. There's a few different ways to get a best fit line. The one that we look at is called a least squares regression line. And the goal with the least squares criterion is we want to minimize the sum of the squares of the vertical distances from each point to the best fit line. So if we drew a whole bunch of squares along with these distances, like this square, we'll make a square here, and we have a teeny tiny one here, and this one's going to be a bit bigger. As we draw in those squares, the sum of the areas of those squares as we go all the way across, you notice I didn't get all of them, but you get the idea. The idea is that the goal is to get the combined areas of those squares to be as small as possible. In other words, we want the summation of the d squareds to be as small as possible. Our ultimate goal is to get an equation that is in the form y equals a plus bx. And yeah, you see my title for the slide, it says slope-intercept form, question mark. Well, it's not exactly slope-intercept form. When we talk about slope-intercept form in algebra class, we're talking about y equals mx plus b. So b's got a whole new meaning here, and m has hit the road, and we've brought in this a. A is the y-intercept, it's our starting point, and b is the slope of the line. So just as we would do in an algebra class, we're going to start by finding the slope and then working back with that to find a y-intercept. To do that, though, we need a couple of sum of squares formulas, and you might remember way back when we were in chapter 2, we talked about an alternate version of computing standard deviation that used the sum of squares formula. To refresh your memory, the sum of the squares formula for x's is we take all of the x values, square them, and add up the squares, and then subtract from it the sum of the x's squared and divide by the number of data values that we had. It's the same idea here. But we need a second formula similar to it. Here's the one we had just looked at. SSX is equal to sigma of summation of the x squareds minus the summation of the x's squared over n. We're also going to need one called SSXY. And in this case, we've swapped out the summation of the x squareds for the summation of the products of the x's and the y's. So for all 10 lines on that table for Quicksell, we're going to take the x and the y values and add them up, or multiply them, and then add the 10 products. And we'll subtract from that, instead of sigma x times sigma x, since we're including a y in here, we'll do sigma x times sigma y. And again, we're dividing by the number of data pairs that we have. We're dividing by n. And if you want, you can think of SSXY as analogous to the change in y, and SSX is analogous to the change in x, because remember that slope is change in y over change in x. It's y2 minus y1 over x2 minus x1. You'll see why shortly why I'm using that analogy. Because the slope is quite literally SSXY divided by SSX. And that will give us the value of b when b is the slope. So we're halfway there. We've got the slope of the line once we've done that calculating. So what point do we want to use to find the y-intercept? Well, we have a whole bunch of choices. We had 10 data values from that 10 ordered pairs from that table, 10 x's with their corresponding y's. But guess what? We're not going to use any of them. What we want to use in order to find the y-intercept, instead of plugging in an ordered pair as x and y, we're going to use x bar and y bar as our point that will help us to find the value of a, where again a is the y-intercept. So we'll figure out what x squared is, what x bar is, we'll figure out what y bar is, we'll plug them in along with the b that we already have, because we did this part first, and that'll give us the value of a. Once we've got a and b, we'll drop them in, and our least squares line will have the form y equals a plus bx. See, here's how this will look for Quicksell. I want you to create in your notes a table that has x and y, but on top of that, you're going to need 2 more columns. Create an additional column that's labeled x squared, and one more column called xy. So that, for example, for the first row, 6 times 6 is 36, so that'll be our x squared. And 6 times 15 is 90, that'll be our value for xy. And at the end, we're going to need to sum up all 4 of the columns. So your x squared column would be 6 squared, and then 20 squared, and then 0 squared, and so on. And your xy column will be 6 times 15, and then the next row will be 20 times 31, and then 0 times 10, and so on. So we'll need summations of all 4 of those columns, and we'll also need values for x bar and y bar. And here is the full table. As we go through this, we add up all of the x's to get 145. We add up the y's for 212. The summation of the x squared values is 2,785, and the summation of the xy's is 3,764. While we're at it, we'll get x bar and y bar. X bar is the summation of the x's, the 145, divided by 10 x's, gives us an x bar of 14.5. For y bar, we'll add up the y's for 212. We already did that. divide by 10y's for a y-bar value of 21.2. To find SSX, Y, and SSX, we're going to plug in with values that we already have. We know for SSXY that summation of the xy's is 3,764. We said that before. Minus the summation of the x's is 145. We'll multiply that by the summation of the y's. That was 210. And there was a total of 10 values here. And this ends up being 690. For the SSX's, the summation of the x squareds was 2,785, and we'll subtract from that the summation of the x's, 145, squared, make sure you square this, over the sample size of 10, and this gives us a value for SSX of 682.5. So SSXY is 690, SSX is 682.5. We plug those into the formula for B, do the division, we're getting a slope of just a hair over 1. It's about 1.01. We'll plug in X bar, 14.5, and Y bar, 21.2. And in order to find the value of B, we find, the value of A. The value of A is 6.56. And so here is our equation for the line of best fit. For any number of advertisements X, we will estimate the number of cars that are sold as 6.56 plus 1.01 times the number of ads that we sell. And that's important because we still haven't answered the question. At 12 TV commercials per week, how many cars should QuickSell expect to sell? Well, this time X is 12. So we're going to replace X with 12. And we do a little calculation and we find 18.68. Now, you can't sell 68 hundredths of a car, and so we would be reasonable. It would be reasonable to round to the nearest whole number. And so we'll say that we're expecting to sell around 19 cars. Couple of quick comments before I give you one to try for yourself. I want you to notice that the one thing that we never had to use in finding the equation of the best fit line was the scatter plot itself. It would have been very helpful to have it sitting close by to make sure that what we were calculating matched what we were expecting to see, but it wasn't a necessity to have it. Everything that we found we did straight through calculating. We didn't ever have to take out the graph paper and graph. The other further thought that I want to leave you with, and this is a very important idea, is the difference between what's called interpolation and extrapolation. When we are interpolating, what we're doing is we're making a prediction within the boundaries of what we already had data for. We made a sales prediction where the blue arrow is. And so we were safe because there were data values as low as 0 and as high as, I believe the highest X was 28. 12 is definitely in the middle. And so it was not unreasonable for us to use the best fit line equation in order to make a prediction. Where we might run into trouble is if we assume that this blue line that we drew is going to continue on forever. This part here, I'm going to change it to red. This part here is an assumption. We're assuming that what was happening up to 28 TV advertisements will continue forever. And where this red arrow is, this is probably like about 45 TV ads. So extrapolation would suggest that if we filled the airwaves with commercials, all day, every day, then we would sell more and more and more cars. And that's simply not realistic. There's a point at which this curve no longer will be a line. That there's some point, and we have no idea where. It might be pretty soon, it might not be for a while, but there's a point at which this is going to start to tail off, and we would have diminishing returns. We don't focus on that in this course. We assume that things that look linear are going to stay linear forever, but in the real world, that's not the case. That eventually things will tail off, or they'll start to skyrocket out of control. And that's part of modeling based on data that we have. That's just that's a regular consideration. And that, if you've been following the news, you can imagine how that might be of interest to us with some of the things going on in the world today. But anyhow, it's time for you to give a problem a try. It is thought that basketball teams that make too many fouls in a game lose the game more often, even if they otherwise play well. So we've got 4 data values here for the number of fouls over and above the opposing team, and we have set Y as the percentage of times that the team with the large number of fouls is winning the game. Logically enough, if you and your opponent have fouled the same number of times, you've got a 50-50 chance of winning the game. If you have fouled twice more than your opponent, your probability of winning has fallen to 45%. 5 more fouls than your opponent, your chances are down to about 1 in 3. And at 6 more fouls than your opponent, your probability of winning, according to this data, is about 26%. So our question is, if a team has fouled 4 more times than its opponent has, what percentage of the time should it expect to win? Well, the first thing we'd better do is create this least squares regression line. We're safe to do that here because 4 is within the x values that we had. When x is 0, x squared is 0. For an x of 2, we get x squared being 4. 5 squared is 25. 6 squared is 36. They add to 65. 65 is a number that we will make use of momentarily. The products xy, 0 times 50 is 0. 2 times 45 is 90. 5 times 33 is 165. 6 times 26 is 156. And they add together to make 411. It's useful to know that the x bar value is 3.25, 13 divided by 4, and that the y bar value is 38.5, 154 divided by 4. To find SSXY, we'll take the summation of the xy's, that's 411, and we'll subtract from it the summation of the x's times the summation of the y's, 13 times 154. There were 4 data values that were 4 data pairs that we were looking at, and this gives us a value for SSXY of negative 89.5. So right away, we're halfway to an indicator that this is going to be a negative correlation. SSX turned out to be positive. And any time that we have a negative divided by a positive, we're going to get a negative. So whatever negative 89.5 divided by 22.75 is, that's going to be our slope, but it's also going to be negative. Negative divided by a positive is a negative. So the SSX came from the summation of the x squareds, which was 65, minus summation of the x's squared. 13 squared is 169, divided by 4. Do the subtraction for 22.75. And the big finish, when we take those two numbers and do the division, we get a slope for our prediction equation of negative 3.93. Using x bar and y bar in order to find a, we find that a is equal to 51.27. And so here is our least squares regression line equation. that y is equal to 51.27 minus 3.93x. Now notice that it's not perfect. It's predicting that if you and your opponent foul the same number of times, that you will win 51.27% of the time. And that's not realistic. I mean, common sense is if you have fouled the same number of times as your opponent has fouled the same number of times as you, it should be equal. It's not, and that's part of the part of the roughness of modeling in this way. We will make the prediction that when we have fouled 4 more times than our opponent has, by plugging in or by replacing the x with 4, 51.27 minus 3.93 times 4 gives us a y value of 35.55. And we'll say that we'll be winning approximately 35.55, or approximately 36% of the time. That's it for this time. We have one more lesson in this chapter, and you'll see that shortly. Thanks for watching. See you next time.